Hi everyone, and welcome to our module on tests of significance. Many clinical studies involve comparing different groups, and when you do this in a clinical study, you often find differences between the groups. For example, two groups in a clinical study might have different mean ages, or they might have different mean values for the blood level of a particular substance. And anytime you find a difference between groups in a clinical study, you have to ask yourself, are those differences real or are they simply due to chance? Remember that in any clinical study, we're studying a sample of the population. We never study the entire population. And so when you find a difference between groups, you have to ask yourself, is that a real difference that exists in the entire population, or did we just happen to sample a group where those differences are present? And so comparing groups to decide whether differences are real or due to chance is very important in medical research. It's also a key element of hypothesis testing, which I talk about in another video. We compare different groups to help us accept or reject the null hypothesis, and this helps us determine whether or not clinical findings are statistically significant. So the main way we compare groups in medical research is by determining a p-value for the differences between groups. This is calculated using statistical methods based on the differences between two groups. And the p-value represents the chance that the null hypothesis is correct. The null hypothesis states that there is no difference between group values. And by convention, if the p-value is less than 0.05, which means there's less than a 5% chance that the null hypothesis is correct, then we usually reject the null hypothesis. This means we reject the hypothesis of no difference between groups, and we accept the alternative hypothesis that there are differences between groups that are real. And I talk about these things in more detail in the video on hypothesis testing. Another way this is often stated in clinical research is that if the p-value is less than 0.05, we say the difference between groups is statistically significant. And by this we mean that the difference is likely real and exists in the entire population and is not due to chance. And a key point to be aware of is that the p-value for comparison between groups is calculated based on the data you collect for each group. So let's imagine we have two groups, Group A and Group B, and we collect a number of data points for each group. And we want to compare the two groups to decide whether or not the differences between groups are real. Remember, the lower the p-value, the more likely the differences between the groups are real and not due to chance. Well, one thing that will influence the p-value is the magnitude of the difference between groups. If there's a very large difference between groups, that means that the differences are more likely to be real and not due to chance, and that will tend to lead to a lower p-value. Besides the magnitude of the difference between groups, other factors affect the p-value, including the scatter of data points and the number of data points. And I talk about all these things in more detail in the video on hypothesis testing. You don't need to know the math behind how we calculate a p-value, but you do have to understand the principle, which is that these characteristics of the data you collect for each group will be used to determine the p-value. And if these characteristics generate a low p-value less than 0.05, then the group differences are considered statistically significant and are likely real and not due to chance. So when you want to determine a p-value for a comparison between groups in medical research studies, there are three key tests that are used. First is the t-test, the second is the ANOVA, and the third is the chi-square. And we'll talk about each of these in the next couple of slides. So before we can talk about specific tests used to determine a p-value, we have to first talk about data types, because different types of data require different statistical tests to determine a p-value. Quantitative data or quantitative variables are data or variables that have numerical values like 1, 2, 3, or 4. So for example, blood pressure is quantitative, serum glucose is quantitative. All of these things have a numerical value that exists for the data point. In contrast, categorical data or categorical variables are data elements where you have to put them into categories like high, medium, or low, or positive or negative, or yes or no. And as we will see, there are different statistical tests used depending upon whether the data in your study is quantitative or categorical. Quantitative variables and quantitative data are usually reported as numbers. So for example, a study might say the mean age was 62 years old. Age is a quantitative variable, and that's why you see a number reported for age. Categorical variables, on the other hand, are often reported as a percentage. For example, 40% of patients take drug A, or 20% of patients are heavy exercisers. Taking drug A is a yes or no thing. It's a categorical variable. Being a heavy exerciser is also a yes or no thing. And therefore, these data are categorical, and they're often reported in studies as a percentage. So now that we understand that, we can talk about the specific tests that are used to determine a p-value for data in a clinical study, and we'll start with the t-test. The t-test is used to compare two mean quantitative variables. It will yield a p-value. So this is done always when you're comparing two groups, like group A to group B. It's not used when comparing 3 or 4 groups. And the comparison has to involve quantitative values like blood pressure or blood glucose. It can't involve categorical values. So to make the concept of a t-test more clear, let's go through an example. Imagine a researcher studies plasma levels of sodium in patients with SIADH and normal patients. The mean value in SIADH patients is 128. The mean value in normal patients is 136. So common questions around a scenario like this is, which test should you use to compare the means? And the answer is a t-test, because we have two quantitative variables of serum sodium and we're comparing two means. And which p-value indicates a statistically significant difference, less than 0.05. Here's the same example, but imagine they tell you that a p-value of 0.01 is reported and they ask you, what does this mean? This is very common in board questions. They want you to interpret the findings of a study. Well, a p-value of 0.01 means there's a 1% probability that the results are due to chance, or another way to state this is a 1% probability that there is no true difference in means and that the null hypothesis is correct. And here's another question. The example is the same, but they tell you the p-value is 0.20, which is non-significant, and they ask you why might that be the case. And the answer could be that you need more patients. Remember that the number of data points, in other words, the size of the sample you are studying, has a bearing on the p-value. And if there are very few patients in a study, that can cause the p-value to be greater than 0.05. If you increase the sample size, it makes it more likely that you will have a smaller p-value, and it gives you more power to detect differences between groups. And I talk about this in detail in the video on hypothesis testing. Okay, let's talk about ANOVA, which stands for Analysis of Variance. This is used to compare quantitative means, just like the t-test, but this is the test you must use when you are comparing more than two means. So for example, suppose we measured the plasma level of creatinine in non-pregnant, pregnant, and postpartum women. We have 3 groups, so there are 3 means that have been determined that have to be compared. So in this situation, you cannot use the t-test because that's for 2 means only. You must use the ANOVA, and it will yield a p-value similar to t-tests. And then finally, the chi-square test is the test that's used to compare 2 or more categorical variables. So anytime the data are categorical, this is usually the test that's required. And remember what I said before, if you're asked to choose a statistical test for a data set, beware of percentages. Even though percentages are numbers, they're often used to describe categorical data. So if they tell you an outcome is 50% in group A and 20% in group B, don't immediately think that because those are numbers, the data must be quantitative. The data could be categorical, and you have to always ask yourself and carefully consider whether the data, which are numbers, are quantitative or categorical. In the video on statistics, I talk in detail about confidence intervals, but let's briefly review this concept now because confidence intervals can tell us something about the significance when we're comparing two different groups. So in the scientific literature, means are often reported with a confidence interval. So for example, if 10 study subjects had their glucose measured and the mean value was 90 plus or minus a standard deviation of 4, we can determine what's known as a 95% confidence interval for this measurement of the mean. It would be equal to the mean plus or minus 1.96 times the standard deviation, which is 4, divided by the square root of n, where n is the number of study subjects at 10. And so if you plug in the standard deviation of 4 and the n of 10, what you get is that the 95% confidence interval for this mean measurement of 90 is 90 plus or minus 2.5. And what this is telling us is that if the study subjects were resampled and we again calculated the mean, we expect that the mean result would fall between 87.5 and 92.5 for 95% of the resamples. This range, which is defined by these numbers here, is the 95% confidence interval. And so the reason I'm talking about confidence intervals in this video is because we can use the confidence intervals when comparing two different groups to determine whether the difference between the group means is statistically significant. And the key point to understand here is that if the ranges defined by the confidence intervals for two groups do not overlap, that means there is a statistically significant difference between the two groups. To make this more clear, let's go through a couple of examples. So imagine that group 1 has a mean value of 10 for some measurement, and the confidence intervals are plus or minus 5. This is a range that goes from 5 all the way to 15. For group 2, let's imagine the mean for the same measurement is 30 plus or minus 4 for the confidence intervals. This is a range that goes from 26 all the way to 34. Well, hopefully you can see that these two ranges do not overlap at all. That means that there is a significant difference between the means for the two groups. This is similar to finding a p-value of less than 0.05 for comparison to the two group means. As a second example, let's imagine that group 1 still has a mean of 10 with confidence intervals of plus or minus 5, but group 2 has a mean of 8 with confidence intervals of plus or minus 4. This is a range that goes from 4 all the way to 12. Well, hopefully you can see that there's overlap between this range and this range, so the confidence intervals define ranges that overlap one another. When this happens, the difference between the two groups can be significant or insignificant. It depends on the degree of overlap. But the key point is that when the confidence interval ranges do not overlap, that means you have a statistically significant difference between the two group measurements. You should also be aware that some studies use confidence intervals when reporting numerical differences between groups. For example, a study might say that the mean difference in systolic blood pressure between two groups of patients was 10 millimeters of mercury. And you can calculate confidence intervals around this difference of 10 millimeters of mercury. And if the confidence interval range includes 0, then there's no statistically significant difference between groups. So this is easier to understand through an example. So imagine a study reports a mean difference between two groups of 10 millimeters of mercury in blood pressure plus or minus 15. Well, this range of 10 plus or minus 15 includes the number 0. So that means there's no significant difference between the groups. This is similar to finding a p-value of greater than 0.05. In other videos, I talk about odds and risk ratios, and you should be aware that some studies report an odds or a risk ratio with confidence intervals. When this is done, if the range defined by the confidence intervals includes the number 1, then the exposure has no significant impact on disease or outcome. So for example, imagine a study evaluated the risk of lung cancer among chemical workers and found a risk ratio of 1.4 plus or minus 0.05. This range defined by the confidence intervals includes the number 1, and therefore chemical work is not significantly associated with lung cancer. This is similar to finding a p-value of greater than 0.05. And I'll finish with this one slide to show you a real-world example of how you can apply the concepts we talked about in this video. So this slide is from a clinical study published in New England Journal of Medicine in 2019. It was a randomized trial of patients with heart failure, and patients were randomly assigned to receive either the diabetes drug dapagliflozin or a placebo. The primary outcome was cardiovascular death or hospitalization for heart failure, and that outcome occurred in 4.9% of patients who received dapagliflozin and 5.8% of patients who received placebo. The authors report a hazard ratio which is similar to a risk ratio, and the hazard ratio for the primary outcome was 0.83, and they show you the confidence intervals which go from 0.73 to 0.95. And you can see that this range does not include the number 1, and so therefore, as we talked about in the last slide, this means that this hazard ratio is statistically significant. To further emphasize this point, the authors report a p-value for the primary outcome of 0.005. This is less than 0.05, so this also indicates that the primary outcome was statistically different between the two groups, and that this is a statistically significant finding. So on your boards, they will sometimes show you the data from a trial like this and ask you to parse out the key elements that help you know whether or not the findings are statistically significant. So any chance you get to look at an actual clinical trial and actual data like what's shown in this slide, you should take advantage of that because it will be very helpful when you sit for your board exams and have to interpret data like what's shown on this slide right now. And that concludes our module on tests of significance.